In the lectures given so far, we have talked about the basic principles of quantum mechanics and also brought up a few ideas about linear algebra which will essentially be used in our next part of the course. What we want to do today is to begin with a few simple algorithms. They are simple because they do not bring out any particularly important point, but they establish the fact that quantum computing has certain advantages over the classical computing. And for that, let's look at what are the very basics of the algorithms that we are going to talk about. The first question is this, that like any other computer, our quantum computer model has quantum registers corresponding to input and those corresponding to output. The difference, as we have pointed out several times, is that while the classical register at a given time can only contain a particular state, the quantum register can contain a linear combination of states. And therein lies the great advantage of quantum parallelism, because corresponding to this linear combination of inputs, our computer can compute functions corresponding to each one of these linear combination components, and the output will be generated by what we have been calling as a quantum oracle. The oracle, as we know, is like a black box computation, very similar to a classical subroutine which we call but don't necessarily detail out in our program. So therefore, a typical model of quantum computation consists of input registers, a target register where the output will ultimately be stored, a black box or a quantum oracle which will compute the type of functions that we want. So this is basically the constitution of the essential computation. But after that comes the most important point of the computation, namely, in any computing we need a readout or a print, whatever you feel like. So we have to extract the required information from the output that we have got. Now that we have pointed out is a very tall order, because even though our output is a linear combination of the results corresponding to the linear combination of the inputs that we have given, if we want to measure the output, there will not be an information about every output corresponding to every input, but one of the random results will come out. Now the question always is that how do you use these random results to your advantage? The first algorithm that we talk about is a simple algorithm which is known as the Deutsch algorithm, where the input is a 1 qubit state which is either 0 or 1, and the output is also a 1 qubit state which is also either 0 or 1. So as we have said, in Deutsch algorithm, input is a 1 qubit which, as we have said, it could be a 0 or 1 or a linear combination thereof. And the output, which is actually a calculation of a function. So we will calculate f0 or f1. Now there are two types of functions that we will be talking about. Of the types of function that Deutsch algorithm calculates, one we'll call as a constant function. Constant function, as we know, is a function whose value is independent of the input that we put in. So therefore, let's say f0 equal to f1 and this could be either 0 or 1. So this will be called a constant function. A second type of function will be called a balanced function, where f0 is not equal to f1, but since our values can be either 0 or 1, it implies if f0 is equal to 0, then f1 will be equal to 1, and if f0 is equal to 1, then f1 will be equal to 0. Now supposing this is a very trivial programming task. Supposing I were to do it by a classical algorithm, how would I determine whether the function that I am calculating, which remember I have said is in a black box, whether the function that we are calculating is a constant function or a balanced function. Now if you are doing it classically, the only way you can do it is to first find out what is f0, get a value which is either 0 or 1, and then find out what is f1 and check whether the f1 value that you get now is the same as the value of f0 that you got in your previous step. So in other words, a classical computation to determine whether the function is a constant function or a balanced function requires two queries. Not a very involved computation, so but we require two queries or two steps. So what does a quantum computing do? This is already a trivial problem, but there is a simple point we are trying to establish, and the point is that in quantum computing I can determine whether a function is constant or balanced by a single query. It's not a great deal of advantage because two queries are not, they don't take normally a lot of time, but is the principle of the thing which is important here. So let me show you this picture, and in this figure you see that there is an input. The input state is 0. I will refer back to this figure time and again. So let's look at that. So if I have an input 0 and I pass it through a Hadamard gate, you know that this gives me input 0 passed through a Hadamard gate will give me 0 plus 1 by root 2. This we have talked about several times. Now this is my input to an oracle. So this is my oracle. So this is what we have been calling as X. And as we know that this input after passing through the oracle is not disturbed. It remains the same. Now the target bit, I start with 1, pass it through a Hadamard gate again, and we had seen earlier that this becomes 0 minus 1 by root 2. This is what we have been calling as the Y, and the result that you get here in the target register is the addition modulo 2 of Y with Fx, which the oracle calculates. So let us look at how does this help. We come back to the question of measurement in a second. So we have seen the input is this. So my input, let me write it as X, Y, and what the oracle is doing is to apply a unitary transformation on it, which will give me the state X undisturbed and Y becomes Y plus Fx. Now since my input register contains X, my X is going to be 0 plus 1 by root 2. This is my input, Now let us look at what do I have in the output register. This y is 0 minus 1 by root 2 addition modulo 2 with fx. So let us analyze this a little more and find out what do I get as a result. The slide tells you the situation, but I will work it out for our convenience. So if you look at it, supposing I expand my input in 2-qubit language, then I had 1 over square root of 2 0 plus 1 into 1 over square root of 2 0 minus 1, the last one was the y. So I get 1 over 2 0 0, the first one came from x, the second one from y, plus 1 0 minus 0 1 minus 1 1. This is what my input was. Now what does the oracle gives? So oracle will give you half. Remember what the oracle does? It keeps the x bit unchanged. The y bit becomes 0 plus fx, so which is f0. So there will be 4 terms here, 1 comma 0 plus f1 plus minus 0 comma 1 plus f0 minus 1 comma 1 plus f1. So this is equal to what? Now you know that when I XOR a state with 0, I get the same value back. So therefore this is 0 comma f0. Now, so this will be 1 comma f1 minus, here I have XORed f0 with 1, which will give me the complement of f0. So let us write that at f0 bar minus 1 comma f1 bar. So this is what is here. Now this output, if we look at the factors, it tells me that I can write it as a half, 0 plus 1, take common, and I am left with then f0 minus f0 bar. Okay. So what I have done here, okay, this is general case. Now what I have done here is I am writing down what happens when the function is constant. So if function is constant, I have f0 equal to f1, so I have replaced f1 with f0, so I get 0 plus 1 times f0, f1 bar is same as f0 bar, so this is what I would get. So look at this now, that since f0 or f1 can take values either 0 or 1, f0 minus f bar of 0 is either 0 minus 1 or 1 minus 0. So what it means is that this term, but for a global phase factor, so I will indicate with this, is given by 0 plus 1 by root 2 and 0 minus 1 by root 2. As I have said that this term could be 0 minus 1 by root 2 or 1 minus 0 by root 2, but in any case it is a matter of an overall global phase only. So therefore now if I were to pass this through a Hadamard gate, so let me bring back my picture. So if this is passed through a Hadamard gate, the first register is being passed through a Hadamard gate. What will happen if the first register is passed through a Hadamard gate? I will get this as 0, and of course this will be 0 minus 1 by root 2. So if my function were constant and I pass the first register through a Hadamard gate, and if I now make a measurement, this will give me the first register will be found to be in state 0. Now let us see what happens if my function is balanced. So look at what the function gives us if it is balanced. Just referring back to my general expression, I had this expression there. Now if it is a balanced thing, then f1 is same as f0 bar and vice versa. So therefore, I can write this as half 0 f0 plus 1 f1, the first two terms I have not changed, they are the same as what is written here. Now since it is a balanced function, my f0 bar is same as f1 and f1 bar is same as f0. So therefore, I write this term as 0 f1 minus 1 f0. Notice again that if you look at what this function is, I take out, for example, you take f0, f0, you notice this is 0 minus 1. Similarly, f1, f1 is again 1 minus 0. So thus, the output is 0 minus 1 by root 2. Let me bring that into plus or minus. This is a global phase problem, as I have told you, 0 minus 1 by root 2. Global phase is immaterial. Now look at what is happening if you pass this first register through a Hadamard gate. Since this is 0 minus 1 by root 2, this is 1. And of course, that second register retains whatever it was. So what it tells me is this, that if I now make a measurement of the first register and the function is balanced, I would get the result to be equal to 1. So summarizing the result, function constant, first register gives me 0, function balanced first register gives you 1. So therefore, all that I need to do is to measure the first register, and if I get a 0, I know that it's a constant function, and if I get 1, it's a balanced function. Now that seems like 50% reduction in the computing resources that we have used. There is a flip side to this. In the classical computing case, where I said that we will need 2 queries, we actually could know what is the value of f0 and what is the value of f1. And it is only by comparing them that we could determine whether it was a constant or a balanced function. What happens in this case, however, is though a single query is good enough to determine whether the function is balanced or it is a constant function, we do not have the information about what the value of the function was. But then that was not our requirement. If the requirement was simply to find out whether the function is constant or otherwise, then a single query of a quantum computer is good enough. What I will now do is to extend this, and introduce the situation where my input, instead of being a single qubit input, my input is a n-qubit input. So therefore, I am interested in functions of n-qubit input, which is represented like this, but the function evaluates to a single qubit. So once again, like the Deutsch algorithm, I have either a constant function or a balanced function. So function is either constant or a balanced. The constant function is obviously clear that for all possible inputs the value is constant, the same. It could be either 0 or 1. I don't care what actually the value of the function is. But for the balanced case, half of the inputs will give you value 0 and the balance half of the inputs will give you value 1. Once again, we don't question as to which input gives 0, which input gives 1. Now, if you look at a classical algorithm to determine it, now let us look at what can we do. So what we could do is to start with some input. Supposing I am, just to illustrate, supposing I want to find out the situation corresponding to 3 qubits or 3 classical bits. Remember that 3 C bits essentially gives me 8 possible inputs. So I have 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0 and 1, 1, 1. So what I can do is to find out what is F0, 0 and I will get some value either 0 or 1. Then change the input, find out what is F0, 0, 1. Having done that, find out whether this value is the same as the other value. Now if it is the same, you still haven't reached a conclusion. If it is not the same, you can stop your computation, because we have said there are just 2 types of functions. So for example, if F00 is equal to 0 and F001 happens to be equal to 1, then you know immediately it was a balanced function because 2 of them did not agree. But in principle I could be unlucky. Supposing this is 0, this is 0, this is 0, this is also 0. I still cannot conclude what type of function it was till I step onto the 5th one. Now when I come to the 5th one, if it is 0, I stop my computation for the simple reason that it is already proved that it is a constant function. So therefore, the possibilities in the worst case of classical computation, you need, if there is a n qubit, you need n by 2 plus 1 trials. That is the worst case scenario. In all likelihood, you are not going to be that unlucky and find out the result much before n by 2 plus 1. So probabilistically, it is quite a reasonable statement to make that a classical algorithm, though in principle requires of the order of n steps, in practice it is likely that will be less. So therefore, in principle it is possible for classical algorithm to require n by 2 plus 1 evaluations before we can conclude whether it is a constant function or a balanced function. In the next lecture, we will see that this extension of n qubit to 1 qubit function, a quantum computer can determine its nature, that is whether it's a balanced function or a constant function in a single query.